Hello everyone, in this video we are going to discuss about loss of prestress due to elastic shortening of concrete. Elastic shortening of concrete happens when the prestress in tendons are released from the tensioning device, which causes the concrete to be compressed. This process reduces the prestress applied to the prestressing tendon. The occurring loss in pre-tensioning and post-tensioning is assessed differently. To evaluate loss of prestress due to elastic shortening of concrete, we need to know how to find prestress in concrete at level of steel. We can find it out by summation of direct stress and bending stress at required level. These are the required parameters to find out the prestress in concrete at level of steel. After calculating prestress in concrete at level of steel, we need to calculate strain in concrete at level of steel, which is the ratio of prestress in concrete divided by Young's modulus of concrete. Then stress in steel corresponding to the strain in concrete is found out by multiplying the strain in concrete to Young's modulus of steel. This is nothing but modular ratio into prestress in concrete at the level of steel. Modular ratio is the ratio of Young's modulus of steel to Young's modulus of concrete. There are different approaches for calculation of loss of prestress. For pre-tensioning, the loss of prestress in the tendons at transfer shall be calculated on modular ratio basis using stress in adjacent concrete. For members with post-tension tendons, which are not stressed simultaneously, there is a progressive loss of prestress during transfer due to gradual application of prestressing forces. The loss of prestress may be exactly computed based on sequence of tensioning. In case of tendons which are simultaneously stressed, there will be no loss of prestress due to elastic shortening of concrete. For members with post-tension curved profile tendons, the cables are curved with maximum eccentricity at the center of the span. In such cases, the loss of stress due to elastic deformation of concrete is estimated by considering the average stress in concrete at the level of steel. The average pre-stress is calculated using the formula average pre-stress equal to pre-stress at support plus two-thirds of difference between prestress at center of the span minus prestress at support, all are calculated at the level of steel. Now let's see how to find loss of prestress in pre-tension beams. A rectangular concrete beam 300 mm deep and 200 mm wide is prestressed by means of 15 number of 5 mm diameter wires located 65 mm from the bottom of the beam and 3 5 mm wires located 25 mm from the top of the beam. If the wires are initially tensioned to a stress of 840 Newton per mm square, calculate the percentage loss of stress in steel immediately after transfer, allowing for the loss of stress due to elastic deformation of concrete only. The modulus of elasticity of steel and concrete is taken. The position of centroid of wires from soffit of the beam is calculated as y equal to 15 number of wires situated at 65 mm from soffit plus 3 number of wires situated at 275 mm from soffit whole divided by total number of wires, which is equal to 100 mm. Now find eccentricity, which is difference between the distance of centroid of the cross section from soffit and distance of centroid of steel wires from the soffit. Now which is 50 mm. Now find out area of concrete, which is B into D, 200 mm by 200 mm into 300 mm. Now find out moment of inertia of cross section, which is BD cube by 12, where B is 200 mm and D is 300 mm. Now calculate pre-stressing force, which is product of initial pre-stress, which is 840 Newton per mm square, and area of cross section of steel, which is 18 number of wires in times area of one pre-stressing steel. Now calculate stresses in concrete at level of steel. At level of top fibers, which is calculated by P by A, where P is 300 kN and A is 6 into 10 power 4 mm square, minus because at transfer above neutral axis, the fibers experience tension. P, which is 300 kN, into E, which is 50 mm, into YT, which is distance between centroid of the top wire to centroid of cross section, which is 125 mm, whole divided by I, which is moment of inertia, which is 45 into 10 power 7 mm power 4. At level of bottom wires, P by A plus, because at transfer below neutral axis, the fibers experience compression, P into E into YB. YB is 85 mm, which is distance between centroid of bottom wires to centroid of cross section, whole divided by I. Now calculate modular ratio, which is ratio of modulus of elasticity of steel to modulus elasticity of concrete. The losses in stress is calculated by multiplying modulus of modular ratio to stresses in concrete at top and bottom fibers respectively. The percentage losses will be loss of stress divided by initial pre-stress into 100. Now let's solve a question on post-tensioning of straight cables. A post-tension concrete beam 100 mm wide and 300 mm deep is pre-stressed by three cables, each with cross-section area of 50 mm square and with an initial stress of 1200 Newton per mm square. All the three cables are straight and located 100 mm from soffit of the beam. If the modular ratio is 6, calculate the loss of stress in the three cables due to elastic deformation of concrete for only the following cases: simultaneous tensioning and anchoring of all cables, successive tensioning of three cables one at a time. First, calculate force in each cable, where P equal to cross-sectional area into initial pre-stress, which is 1200 Newton per mm square. Now calculate area of cross-section, which is B into D, and calculate moment of inertia, which is BD cube by 12, and eccentricity, which is the distance between centroid of cross section to centroid of steel, and calculate y, which is the distance between the level of steel to centroid of cross section, and calculate the stress in concrete at level of steel, which is calculated by P by A plus PE into Y whole divided by I. In first case, under simultaneous tensioning and anchoring of all three cables, there will be no loss due to elastic deformation of concrete. In second case, when the cables are successively tensioned, when cable 1 is tensioned and anchored, there will be no loss due to elastic deformation. When cable 2 is tensioned and anchored, there will be loss in cable 1, which is given by product of modular ratio into stress in concrete at level of steel. When cable 3 is tensioned and anchored, there will be loss in both cable 1 and cable 2. Total loss stress due to elastic deformation of concrete is calculated in cable 1. There will be loss due to tensioning of two cables, which is 16.2 plus 16.2. The cable 2 experiences loss only one time during tensioning of third cable. The cable 3 does not experience any loss. So the average loss of stress considering all three cables will be summation of the losses in all three cables all divided by number of cables. Now let's see how to solve numerical problem on post-tensioning of curved cables. A post-tension concrete beam 100 mm wide and 300 mm deep spanning over 10 meter is stressed by successive tensioning and anchoring of three cables 1, 2 and 3 respectively. The cross-sectional area of each cable is 200 mm square and initial stress in cable is 1200 Newton per mm square. Modular ratio equal to 6. The first cable is parabolic with an eccentricity of 50 mm below centroidal axis at the center of the span and 50 mm above the centroidal axis at the support section. The second cable is parabolic with zero eccentricity at the support and eccentricity of 50 mm at the center of the span. The third cable is straight with uniform eccentricity of fan 50 mm below centroidal axis. Estimate the percentage loss of stress in each of the cables if they are successively tensioned and anchored. First, calculate force in each cable, which is given in the question. Now, calculate area of cross section. Then, calculate moment of inertia by BD cube by 12, where B is 100 mm and D is 300 mm. When cable 1 is tensioned and anchored, there is no loss of stress due to elastic deformation of concrete. When cable 2 is tensioned and anchored, there will be stress in cable 1, which is calculated at level of cable 2, both in support and at midspan. Stress at support section equal to P by A, where P is 240 kN and A is 3 to 10 power 4 mm square. Stress at center span equal to P by A plus P into E, eccentricity is 50 mm, into Y, which is 50 mm, which is distance between the centroid of the cable to centroid of the cross section, all divided by moment of inertia. The average stress in steel is calculated using formula stress at support section plus two-thirds of difference between stress at midspan and stress at support section. The loss of stress in cable 1 is calculated by multiplying modular ratio and average stress in concrete. When cable 3 is tensioned and anchored, there will be losses of in stress in both cable 1 and cable 2, which are calculated as shown in the below table as explained earlier. Finally, calculate the percentage losses of stress in each cable.